Today I want to consider the model reference approach to building a adaptive control system. What you can see on the screen is a simulator that implements the numerical example that was presented in my previous lecture. First of all, I want you to see the best guess controlled plant. Then I want you to see the true controlled plant that is different from the best guess controlled plant. Then I want you to see the reference model. This is the reference model. I want you to note that the reference model is fully decoupled system that has required dynamics for the first channel and very similar dynamics for the second channel, but the channels are completely independent. And then I want you to see the linear model following circuitry that was designed, and I gave you full explanation how this linear model following circuitry was designed. Now, in the linear model following circuitry, there is a way to add two components of the adaptation mechanism to the control effort. But as you can see, both components are not connected to the control effort. And therefore, the adaptation mechanism is disabled. And therefore, don't look at this drawing yet. You will see it in a second. I want to add a step signal to the first input of the reference model. The reference model is decoupled, and therefore the linear model following system was designed, and therefore it is our expectation that the control plant with the linear model following circuitry, with the feedback, will behave exactly as the reference model. Let's see what happens. System and go. And what you can see is a completely different picture. The red is the output of the reference model. Look, it's supposed to reach value of 1. It's supposed to look like the first order system response, and it's supposed to be like you can see in red in this drawing. In the second drawing, you also see the correct representation of the output of the reference model. The system is decoupled, and we are applying excitation only to the input number 1, and therefore, in the output number 1, you're not supposed to see any response. Look, if I would apply the step input to the input number 2 of our system, what will happen is this: system and go. What you can see, this red is the response of the reference model, which is correct response. The output of the reference model in the output number 1 shows no response. This is 0 because system is decoupled. But what about these blue signals? Look, system, go. What happens with these blue responses? The system's supposed to be decoupled. We performed linear model following design. We can expect that the controlled plant with its control system will behave exactly as a reference model. It does not. It does not. Because you can see clearly that this response is quite different from the response of the reference model for channel 1. For channel 2, you're not supposed to have any non-zero response in the output number 1, but output number 1 features some kind of non-zero response. So our attempt to force our control system to behave as a reference model failed. And you understand why it failed. It failed because the true control plant is different from the best guess control plant that was used in order to build the linear model following system. What do we do in this situation? In this situation, it is clear that we have to engage the adaptation mechanism. We have to connect the adaptation signal to, or add adaptation signal to the control effort. You know, adaptation signal in my case is a vector with two components, component 1, component 2. What will happen now? The adaptation mechanism is engaged. System, go. And what you can see is virtually a perfect picture. In the output number 1 of the reference model and the controlled system, you see virtually no discrepancy. Maybe in the very beginning there is some kind of difference between the control plant and the reference model, but this difference immediately disappears. As far as the second output of the reference model and the control plant, for the reference model we have 0 response, and response for the control plant shows some oscillatory process that converges to 0 with time. And the magnitude is very small, very small. So we can clearly state that the system with the adaptation mechanism behaves exactly as it is expected to behave. Now let me apply input signal to the input number 2 of the reference model, and the picture will be reversed. System, and go. So what you can see now, that the output number 2 of the reference model and the control plant completely coincide, and in the output number 1 of the reference of the control plant, you can see oscillatory process that has quite small magnitude, and it converges to 0. The red line, of course, is the output signal of the reference model that's supposed to be equal to 0. So I guess this simulation shows you the efficiency of our model reference design. What I want to do now, I want to get into the control plant definition, and I want to inject a sinusoidal disturbance signal. Look, this is the sinusoidal disturbance signal, and I am applying it to the input number 1 of the control plant. And it's a sinusoidal signal. And let me now disengage, disconnect the adaptation mechanism. So what you're supposed to see? You will see that the reference model still behaves perfectly if we would apply step to its input number 1. The reference model is decoupled. You will see a response only in the output number 1. There will be no response in the output number 2. You know that the control plant is affected by the disturbance signal. You can assume that this is an earthquake or air turbulence or something of this nature. But since reference model is implemented in a simulator, the earthquake cannot affect the reference model. And the reference model will behave still perfectly, in spite of the disturbance applied to the input of the controlled plant. Again, this is the sinusoidal disturbance injected in the input of the control plane. So what we're supposed to see? System and go. What you can see is the sinusoidal response in the output number 1 of the control plant and in the output number 2 of the controlled plant. However, the reference model shows no impact of this disturbance. And this happened with the adaptation mechanism disconnected. Now I will get into linear model following circuitry. I will reconnect the adaptation signal, and let's see what will happen. System and go. Listen, don't be too much surprised. The purpose of the adaptation mechanism is to force the control plant to behave as a reference model. It's forcing it to behave as a reference model. And therefore, as far as the system with the reference model and the adaptation mechanism is concerned, look, the output number 1 shows virtually no impact of the disturbance. The output number 2 shows the effect of disturbance. It shows some kind of high-frequency oscillatory process affected by the disturbance. But what you can see is this. The magnitude is very, very small, and the response to disturbance decreases with time. So the conclusion should be this. The model reference mechanism, the model reference circuitry, offers a powerful way to reject disturbance applied at the controlled plant. Let me apply signal to the second input of the reference model. This is the step signal. The system will work now like this. Again, the output number 2 of the reference model fully coincides with the output number 2 of the controlled plant. Now, the output number 1 of the reference model shows 0 value, what it's supposed to be. However, due to the disturbance, the response in the output number 1 could be observed. It's a high-frequency signal that converges with time. And you also should realize that its magnitude is quite small. Again, to enhance the learning process, let me disconnect the adaptation mechanism again. And what will happen, you will see right now. Yeah, without adaptation mechanism, disturbance has profound effect on our system. With the adaptation mechanism engaged, we're getting exactly what we were expected to see. What I want to do now is to show you another simulated experiment. I will show you what happens if controlled plant has parametric drift file, and the file is called drift. It's exactly the same system. The input step I will apply to the input number 1 of the reference model. The reference model is the same, the coupled reference model. The true control plant has been changed. Look what I did in addition to the control plant that you saw before. look at this parameter. Initially, the state variable y1 was applied to the appropriate part of the input of the state equation of the control plant. I modified this control. I modified this state system, state variable system. Look, now, in addition to this constant element of the matrix A, of the fundamental matrix of the control plant, I have addition, a ramp. It's a ramp signal with a slope of 0.05. And what you can conclude now, that instead of 3.2, I have 3.2 plus some kind of addition, increasing addition, some ramp is added to this particular element of the fundamental matrix. How this supposed to affect our system? First of all, I will get into the linear model following circuitry, and I will disengage the adaptation mechanism. The adaptation signal is not connected to the reference signal. Look what happens. System, go. And don't be surprised. As far as the reference model is concerned, we have the expected response of the reference model. The signal is applied to the input number 1 of the reference model. So in the output number 1, we can see this first order type response. The second output of the reference model does not show any non-zero signal. However, we have these signals clearly in the output of the control plant, and they could be traced only to the parameter drift, to the drifting parameter of the control plant. Because of this drift, we have this effect. What I will do now, I will engage the adaptation mechanism. Now adaptation mechanism is engaged, and the result will drastically change. System and go. Look, parameter drift, as you can see, has no effect on the output number 1 of the reference model, of course, but also on the output number 1 of the controlled plant. Parameters of the plant change, show some drift. The response does not change. As far as the effect on the output number 2 of the control plant, the magnitude is very small, and the signal converges to 0. So the system slowly begins to behave as a decoupled system. Look what if I will apply signal to the input number 2 of the reference model, system and go. The situation is also very clear to explain. The output number 1 or output number 2 for the reference model and for the control plant behave in the same way. However, the output number 1 of the control plant is very small, and it has tendency to converge. Now, I want you to realize that when it comes to parameter drift, there is certain limitation, because parameter drift is supposed to have certain rate of change, and the adaptation mechanism supposed to have its own rate of affecting the control plant. So it's a kind of race between the adaptation signal and parameter drift. So I would tell you, if I would increase the rate of change of the parameters of the control plant, our adaptation mechanism may not be able to follow to address this parameter drift. But as any educational example, what you see is kind of exaggerated effect, and in real life you still can rely on the adaptation mechanism in your system. Let me close simulation and let me get into my lecture that I'm supposed to show you today. Today I want to show you another example on the development of adaptive model following system using the hyperstability and positivity approach. And again, our definition of the system is a state variable definition, and I will talk to you later about the transfer function definition. What you can see here is a cross-coupled controlled process, and this is supposed to be the true equations for this controlled it's supposed to be the true equations for the controlled process. You may tell me that true equations may not be known to the user. This is true. But in the simulation environment, we still have to represent the true process. So I have this true process defined. The state variable definition is x dot is equal to ax plus by, v output is equal to cx, and we're dealing here with a process that has 4 states and 2 outputs and 2 control efforts. So there is nothing wrong about this control plan, except instead of the true state variable definition, we have the best guess definition. This is not accessible to you and me. We will use it only to facilitate our simulation study. Best guess plan definition. Based on this best guess plan definition, you may see that the fundamental matrix is not a matrix typical of a decoupled system. No, it does not consist of 2 independent blocks. This is one block. This is another block. But look at this signal. Look at this parameter. Because of this parameter, decoupling is not available. Our system is not a system that could behave as a decoupled system unless we will work on it. The next what you can see is the desired closed loop system. The desired closed loop system. This desired closed loop system is surely a decoupled system. The matrix, fundamental matrix of the desired closed loop system indicates that the system is the decoupled system. The system is the decoupled system. And of course, the dynamics of the system is quite different from the dynamics of the existing, even best guess control plan. And I'm not sure what happens with the true control plan. So, how to force the control system to behave as a decoupled system? Well, we have to introduce a state variable controller. It's part of the linear model following design. Look, the desired closed loop system transfer function, desired closed loop system fundamental matrix is matrix A minus B times Kp. Kp is the matrix of the state variable controller. Now, fortunately, matrix B is available. Fortunately, matrix A is available by the best guess, and therefore we can find matrix Kp from this equation. How we do it? Look, I do simple subtraction. Matrix B times Kp is equal to A minus A closed loop. So it looks like from this equation we should be able to find matrix Kp. But since we deal with matrices, it's not that easy to do, or not that straightforward to do. So I will multiply left-hand side of this equation and right-hand side of this equation by matrix B transposed times B transposed. So this is what I have now. Take a look at this B transpose times B. B is a 4 by 2 matrix, but B transposed times B is a 2 by 2 matrix, and hopefully we should be able to invert it. So look what we do. If I would multiply left-hand side and right-hand side now by B transposed B in the power of -1, I will be able to find matrix Kp. And this is what I have. Matrix Kp is equal to B transposed B in the power of -1 times matrix B transpose times A minus A closed loop. And since I have good, reliable software tool, and since I am proficient with this software tool, I guess this is what I'm getting. Definition for Kp. What I will do now, I effectively achieved the decoupling behavior. How I know I achieved the decoupling behavior? Well, if you want, I know matrix Kp, I know matrix A, I know matrix B. A minus B times Kp will be exactly this matrix. Our system will become a system with a block diagonal fundamental matrix. This matrix is surely decoupled, or the system is surely decoupled. So what I am trying to do now is something else. I looked at the design specifications, assuming that I looked at the design specifications. And design specifications to require me to have eigenvalues -8 plus -j for each of the dynamic channels, and I want systems still to be decoupled. This is how I would define the reference model. The reference model now will represent a decoupled system with the dynamics consistent with -8 plus -j eigenvalues for each of the channels. This is the fundamental matrix of the reference model. This is matrix B of the reference model, and this is matrix C of the reference model, which means that the first state variable and the third state variable I will use as the outputs. Now we have to concentrate on finding matrices Km and Ku from specific known to you equations for linear model following design. And the only what I can do at this point is to find matrix Km and to find matrix Ku. How I'm doing it? I'm doing it using the pseudo-inverse of matrix B. Well, I'm using pseudo-inverse, and you can read more about pseudo-inverse. But one way or another, I have matrix Km defined, and I have matrix Ku defined. Now, I have matrix Kp earlier defined, I have matrix Km defined, and have matrix Ku defined. And you know how the configuration of the linear model following system looks like. However, if I would apply this matrix Ku, Km, and Kp to the best guess definition of the control plane, I would be in great shape. However, the control plane is the true control plane. And if I would apply this definition to the true control plane, I surely know that dynamics will be different from expected. There will be no decoupling in the system. This is it. And because of this, what we have to do is to work on the design of adaptive model following system. And you know how we do it. First of all, we have to introduce filter G into the linear time invariant part of the equivalent nonlinear negative feedback system. We talked about this in lengths in the previous lecture. But nevertheless, this is the transfer function of the linear time invariant part of the system. And we have to solve for matrix D to make sure that this linear time invariant part will be strictly positive real. And we have to use for this purpose the Lyapunov equation. In the Lyapunov equation, this is a closed loop transposed, this is a closed loop transposed. This is supposed to be any arbitrary positive definite matrix taken with a minus sign. And I always use unity matrix. And matrix P is the solution of the Lyapunov equation. And Lyapunov equation should be solved best by using a computer tool. And I used computer tool and I got this result. Now, if you would take a look at this linear time invariant part of the system, I have matrix G and I have matrix B. And because of this, matrix P has to be converted into matrix D. I have to extract matrix D from matrix P, and this is how you will do it. Matrix D is equal to B transpose times P. And only what you can, what you're supposed to be see now is the matrix D as it is. It is a 2x4 matrix. When matrix D has been defined, it is time to define vector V that consists of intermediate variables. Vector V is supposed to be the output vector of the linear time invariant part now. It's equal to G times E, or G times Z minus X. What is Z? Z is the state vector of the reference model. X is the state vector of the control plane. So V is equal to matrix G times this column. But this column I call E1, E2, E3, and E4, where E stands for error. And if I would perform this multiplication of matrix G, by vector of errors, I'm getting this result. So vector V has only two components, and both components have very straightforward definition. And later, when we will be building our system, we should be able to define V1 and V2 by independent setups. So as far as I am concerned, we handled successfully the linear time invariant part. Now what we have to do? Now we have to handle the nonlinear time varying part. We have to enforce the Lyapunov equation on it. And this is how we do. Look, according to what I told you in our previous lecture, matrix function phi1 and matrix function psi1 should be defined as a positive definite matrix H times vector V times state vector of the controlled plant transposed times positive definite matrix G. And matrix function psi1 is defined as a positive definite matrix M times vector of intermediate variables V times the input vector of our system, which happens to be reference transposed, times matrix N, which is a positive definite matrix. And you know that I always want our results to be as simple as possible. And for H and M matrices, I will use unity. Matrix G and matrix N, I will choose as 0.1 or just positive constant times unit matrix, 0.1 or just positive constant times unit matrix. And if this is the case, look, I want to compute V times X transposed. V times X transposed is a 2x4 matrix, and each component of it could be defined by a independent setup in the simulator. And what you can see here is V matrix times R transposed, V1, V2, and this is R1, R2, and you can see now matrix, 2x2 matrix, and each element of this matrix could be defined by an independent setup in our simulator. And this is our matrix phi. It is equal to 0.1 times V times X transposed. And this 0.1 could be replaced by any positive number, by different positive numbers. And when I will be running simulation, I will be considering many alternatives to 0.1. And this is how matrix psi is defined. 0.1 times the matrix comprising products V1, R1, V1, V2, R2, V2, R1, V2, R2. The best what I can do at this point is to show the simulation of our system. You know, I don't want to get into all this little detail, but what you can see here is the control plant. The way I simulate this control plant, it has two inputs, it has two outputs, and it has 4 state variables. This is the reference model. In the reference model, I have 2 inputs, and I have 2 outputs. I even don't care about the state variables. State variables could be found inside. And as a matter of fact, the way our reference model is defined, it does have 4 state variables, but state variable number 1 and state variable number 2 are used as outputs. This is my definition of the reference model. This is the matrix Km that picks up state variables of the reference model and converts them into the signal injected into the input of the control plant. This is matrix Ku. Matrix Ku picks up the inputs R1, R2, converts them into particular components of the control effort, and applies them to the input of the control plant. And finally, these 4 state variables of the control plant, they are picked up. I have a state variable controller with matrix K, P implemented here, and of course I'm getting out of it 2 components of the control effort. The adaptation mechanism is designed, and to get this adaptation mechanism, I have to integrate matrix function phi and matrix function psi, and eventually create 2 components of the adaptation signal. Here you can see that the adaptation mechanism is disconnected. And you see the consequences of this disconnected adaptation mechanism. Red represents the output of the reference model. The output of the reference model is a response to a rectangular signal, a rectangular wave, and the response is supposed to have 0 overshoot and require settling time. So, believe me, the output of the reference model behaves exactly as it is supposed to behave. In the drawing number 2, you have the second output of the reference model, but our reference model is decoupled, and because of this, you see 0 in the output of the reference model. If I would apply input signal not to the first, but to the second input of our system, situation will change. And the change situation is shown here. We expect our system to be a decoupled system where output follows the output of the reference model. The output of the reference model, red, you can see it here. It's perfect because the reference model is not affected by incomplete knowledge of the control plane. However, the blue part, the output of the control plant, due to the fact that a control plant is different from the best guess plant, it shows this oscillatory process and basically does not behave properly. The first output of the control plant also shows inappropriate behavior because our decoupling, simply speaking, does not work. The next, what we did, we engaged the adaptation mechanism, and as we engaged the adaptation mechanism, I see virtually no difference between the response of the reference model and the response of the control plant. As far as the response of the second output of the control plant, first of all, it is very small by magnitude, and it converges to 0, which means that our design works properly. Now, I excited the second input of the reference model, and what happens here is the second output of the reference model is very consistent with the output of the control plant, second output of the control plant number 2. Virtually nobody can see the discrepancy. But the output number 1 of the control plant, first of all, it is very small by magnitude, and as you can see, it converges to the to 0 effectively, or converges to the output of the reference model. So I can tell you that with the decoupling mechanism engaged, with the adaptation mechanism engaged, our decoupling design works perfectly. You know what I did? I injected disturbance into the control plant, and you can see it right here. Take a look. Take a close look. Do you see the sinusoid is added to the input number 1 of the plant, and this sinusoid is added to the input number 2 of the control plant? But you understand that disturbance could be earthquake, could be fluctuation of temperatures, could be turbulence of air. It cannot affect, cannot reach the reference model, because reference model is nothing but a simulator, a subroutine running within our computer. So look, the adaptation mechanism is disengaged, and you can see that the reference model works fine, but the control plant shows this oscillatory process and shows you quite persistent oscillatory process in the output number 2. If I would apply signal to the input number 2 of the control plant, you will see that the oscillatory process affects the output number 2, and output number 1 is just a sinusoidal signal. So without adaptation mechanism, our system does not work properly. The adaptation mechanism is engaged now. Look, it is engaged. You see virtually no difference between the output of the reference model and output of the control plant. For the output number 2 of the control plant, you see converging signals and very small magnitude. Very small magnitude. And if I would apply input to the input signal to the input number 2 of the reference model, the second output of the reference model shows very decent behavior. It is consistent with the response of the reference model. And in the output number 1 of the control plant, you can see this oscillatory process. It is actually converges, and this process has very small magnitude. So the adaptation mechanism does work, does do its job. Let me do this now. Let me make a couple of statements. Let me make a couple of statements about the transfer function definition. You know, it's unreasonably complex. I used a book by Landau, and I tried to work through the equations, and I guess I can do it, can work through these equations. But to my class, to you, it would be cruel and unusual. I invested considerable time. I tried to simplify these equations, and I couldn't. So what would you do in a situation like this? First of all, if you will work in industry, you will not care about how much time you have to invest because you will be paid for doing it. And I think you will find a way how to develop a adaptive model following system defined by transfer functions in the transfer function definition. However, there is another alternative. What you can do, you can create a state observer, and you know how to create a state observer. With the created state observer, you will have information on the state variables of the control plant, and then I guess you will be able to do the state variable definition-based system design. Before I will get to the test questions, I would like to show you some simulations result on the example that you saw before. I will get into the simulator. File, and I'm doing the not this one, opening. Yeah, the system is open. And it's a real simulator. Look, I can move things around. Can do a lot of things here. First of all, I want you to realize that this is the control plant. This was the original best guess plant. And this is the new plant, which is the true control plant. This is the state variable controller with matrix KP. This is the reference model, fully decoupled reference model. This is the implementation of matrix KM in the simulation environment. This is the implementation of matrix KU. This is the adaptation mechanism. And this adaptation mechanism has several stages. First of all, we're extracting the error, then we create vector D, and so on. It's every single stage in the development of the adaptation mechanism has been performed. It's a fourth order system, and I guess it is considerably hairy. What I want you to see now is the following. First of all, I will disengage the adaptation mechanism, and I would apply input signal to the input number 1 of our system, and you will see output of the reference model versus output of the control plant, and output number 2 of the reference model versus the output number 2 of the control plant. System and go. Well, you can see very clearly that the outputs number 1 are different from each other. The difference does not disappear with time. The reference model has the response that is correct. The control plan has response inconsistent with the reference model. And from this drawing, you can see, from this response, you can see that there is no decoupling in our system. There is no decoupling because the input was applied to the input number 1, to the channel number 1, but you can see this blue response, blue signal in the output of channel number 2. If I would change the application of the input signal, a similar thing will happen. Yeah. Now the output number 2 of the reference model and the control plant look even worse. The reference model is still good, shows good response, expected response. However, the response of the control plant now shows this oscillatory process. It's not a good case. And of course, there is no decoupling operation because the input was applied to input number 2, but you can see clearly response in the output number 1. What I will do now, I will engage the adaptation mechanism and I'll show you what will happen. System and go. You can see very good result. Very good result. Now the input is applied to the input number 1 of the system. Virtually there is no difference between the responses of the reference model and the control plant. As far as the output number 2 is concerned, the magnitudes are very small, and you clearly see the converging discrepancy between the two state variables, and this discrepancy effectively converges to 0. So this is a very good result. And now I will add the input signal to the input number 2, and I will do system and go. So now you can see that in the output number 2, response of the reference model is virtually identical to the response of the control plant. In the output number 1, the magnitude of the response in the output number 1 of the control plant, it's supposed to be 0. It's not 0, but its magnitude is very small, and it converges to 0 with time. So our decoupling goals are successfully achieved, and basically we could report that model reference approach works all right. What I will do now, I will inject disturbance in the system. Look what I'm doing. To the input of the control plant, I inject a sinusoidal signal. Look at the sinusoidal signal is injected in the input of the control plant, and I have a sinusoidal signal injected in the second input of the control plant. Look, I will disengage the adaptation mechanism. And look what will happen. System and go. Yep. It's very obvious that the behavior of the control plant is affected by the sinusoidal signal injected, while the behavior of the reference model is not. Let me apply signal to the input number 1 of the system. System and go. Yeah, you can see very clearly that there is a very unpleasant discrepancy between the output number 1 of the reference model and output number 1 of the control plant, and there is signal that effectively does not belong to the output number 2 of the system. This sinusoidal disturbance causes the signal. What I will do now, I will engage the adaptation mechanism, and you will see what happens. System go. Yep. You can see that effect of disturbance on the output number 1 of the control plant is significantly reduced. I can work on adaptation gains, and I may get rid of even of those tiny fluctuations that you may observe. For the reference model, for the output number 2 of the reference model, I still have 0. For the output number 2 of the control plant, I have this ugly sinusoidal, well, it's not even sinusoidal, ugly periodic signal. Its magnitude decreases with time, and its magnitude is quite small. Look what will happen if I will remove the adaptation mechanism again. Removing adaptation mechanism, system, and go. So look, the magnitude is something like 6 units with the adaptation mechanism engaged. The magnitude is much, much smaller. Now it is 6. System, go. Now it is 0.06. The magnitude is reduced, what? By almost by 20 decibels. Excuse me, by 40, 45 decibels. Anyway, now what will happen if input is applied to the input number 2, system, and go? Yeah, the same situation happens. The disturbance affects the response of the control plant, but the effect is very, very small. You may or may not see this ripple. As far as the response in the output number 1, it is very small by absolute value, and it converges to 0. And of course, if I'm not happy with these results, I still can. I have 2 ways of handling it. One way is to change adaptation gains. Okay, do you remember I was using 0.1, I told you? I can use 10 and I can use 20. This is one of the approaches. The second approach, if you would recall solving the Lyapunov equation, in the right-hand side of the Lyapunov equation supposed to be a positive definite matrix Q with minus sign. I used unity. Nobody would stop me from using different definitions for matrix Q, and I probably would achieve further improvement of the adaptation results. What I am doing now is I am getting to the questions for the test, because our next class will be a test, and I expect you to spend 2 hours for this test. You will have to do some analytical work, you will have to describe certain things, and you have to do some calculations. For your calculations, make sure that you have your calculators. They may be needed, but computer tools will not be used, because I will never give you anything greater than the second order. So, what should you expect during the test? Number 1, I will give you a specific configuration of a model reference system, and you will have to identify this system. You have to describe the principle of the system operation. You will have to describe the functionalities of the individual blocks. The second type of problems, you will have the mathematical description of a model reference system, and I would require you to utilize local parametric optimization to obtain adaptation mechanism of the chosen system parameters. For example, of parameter B5, you will have to give the adaptation mechanism. Number 3, you will have the mathematical description of a model reference system, and you will have to obtain the equivalent nonlinear negative feedback system, and you will have to define every component of the system. But I promise that you will not go beyond a second order 2x2 system. Number 4, given the mathematical description of a model reference system, I will give you a Lyapunov function for the stability-based system design. You will have to obtain the adaptation mechanism. And the adaptation mechanism have to be defined by very explicit equations. And number 5, I will give you mathematical description of a model reference system. You will have to apply the hyperstability positivity approach to obtain the adaptation mechanism for the system. So I wish you good luck for the test. It is a closed book test, people. Closed book test. And since there are few people in class, it will not be a big deal for Min to make sure that you are all doing things right. All right? So you take care.